So we're starting thermochemistry for this unit, and before we can talk about thermodynamics, we have to talk about energy and what it means. And most of this is just a memory game for you, you already know. Energy is anything that has the capacity to do work, and you know work in terms of physics is a force acting over a distance. Therefore, energy equals work, which equals force times distance. And in chemical systems, we talk about three processes in energy exchange. The first one is in heating and cooling, and the second is in phase transitions, and the third in chemical reactions. Remember that heating, cooling, and phase transitions are physical changes, and they don't have nearly the energy quotient that a chemical reaction would have. So, talking more about energy, kinetic energy is the energy of motion, energy that's being transferred, and that's equal to 1/2 mv squared, where m is mass and v is velocity. And potential energy is the energy that's stored in an object. We can think of it as energy based on the position of something. And in chemistry, we're really talking about the energy, the potential energy in chemical bonds, or the potential energy of electrostatic charges. And thermal energy is associated with temperature. It's a form of kinetic energy. The SI unit for energy is the joule. In the English system, the equivalent unit would be the calorie, and that's a calorie with a small c. It's the amount of energy needed to raise the temperature of 1 gram of water 1 degree C. If you were to look on the side of your Fruit Loops box this morning, you would see the caloric content listed with a capital C. That is the layperson's unit for a kilocalorie. And so there are 1,000 calories in 1 kilocalorie, and we base our nutritional information off of the kilocalorie. All right. So let's think about, for ease and simplicity, as energy as a quantity that an object can possess. Now, heat and work are the two different ways that an object can exchange energy with other objects. Remember, heat is really the flow of energy from one object to another object. So energy can be exchanged this way. If energy is the ability to do work, we can have kinetic energy, which is due to motion, and that would be associated with thermal energy, or potential energy due to the composition or position, and that has to do with the positions of the electrons in the nuclei. I'm just going to go right over the forms of energy because you can read and you've seen this before. And I'm going to talk about conservation of energy just really quickly. You know that energy can neither be created nor destroyed with ordinary means. There are extraordinary means, but we're not going to encounter them in this class unless something goes horribly, horribly wrong. What I would like to talk about is the most important part of this lesson, and that is you getting straight in your mind the new terms for you, and that is the universe, the system, and the surroundings. When I say the universe, I do not mean that part of our environment that contains the Milky Way. I'm talking about the universe that only has the system and the surroundings. And when I'm talking about the system, I'm talking about the process or the thing that we are studying. And that is a very small, confined definition. And then everything else is the surrounding. And that's huge and broad. Lots and lots of things are the surroundings. On the bottom of the page, I have written the dissociation reaction for solid sodium chloride, an ionic compound, in water. When it dissolves, it forms the sodium ion and the chlorine ion. The system in this case, can everybody picture when you throw in a couple of grains of salt into some water and it dissociates? The system in this case is the sodium chloride and its ions. everything else, including the solution that it makes, are the surroundings. Are you good there? Okay. Now, in chemistry, and not always in science, but in chemistry, we always take the perspective of the system. It's almost like we jump in there and just look from the inside out. Are you good there? So when we talk about energy being exchanged from the system in the surroundings, we take the perspective of the system. Physics very frequently, and in engineering, does the opposite. Okay. Now, because we are ordinary and we conserve energy, you need to realize that the energy changes in the system and the surroundings have to equal 0. Now, let's say that when we dissolve that sodium chloride, 100 joules of energy left the system to the surroundings. Right? It left the system. That's a loss to the system. We would give that 100 joules a negative sign, and that negative sign would be telling us that the energy left the system and then was picked up by the surroundings. And the surroundings energy gain would be a positive sign. Everybody good there? So you can see that the energy of the universe must be 0, because if one thing loses, the other thing gains. Everybody good there? It would be wonderful if I could get you to think of the sign in all of thermodynamics as nothing more than an arrow. The sign is an arrow showing you the direction of energy flow. If the system loses energy, that would be an arrow pointing out. That would be a negative sign. If the system gains energy, that would be an arrow pointing in. That would be a positive sign. Can you go with that? Okay. All right. So the only way energy can be exchanged is by a change in heat or work being done. In chemistry, almost exclusively, we focus on the change in heat. That's what we talk about as what's going on. I'm sorry, I skipped the internal energy. Internal energy is the total energy of the system itself. That's the amount of energy that's available to be exchanged with the surroundings. It is abbreviated E, and it is added, it is 2 components. One is heat, which we give the unit Q, and the other is work W. All right, so heat we can track, work is harder to do. Heat is the exchange of thermal energy between the system and the surrounding. Heat is only exchanged when 2 objects are at different temperatures. And when 2 objects are at different temperature, the heat always goes from the hot to the cold, despite what you think. I'm here to tell you that how many people have gone outside in our version of winter with bare feet? Because it's our version of winter and you're not going to die dead if you go outside. But if you walk outside like on your sidewalk in your bare feet in February, you would be incorrect if you thought, I can feel the cold just coming up from the ground and creeping up my legs. Because what you're actually feeling is what? The heat leaving you as you are trying to heat up the concrete. Everybody good there? Always goes from hot to cold. When does it stop? When 2 things reach thermal equilibrium. When the 2 objects reach the same temperature. Thermal equilibrium. Now, you can see by that example that you have to have a lot of other things to think about, like mass for one thing. All right. Now, in chemistry, the work portion of internal energy only has to do with gases and only has to do with Boyle's law. Remember, Boyle's law is pressure and volume, and they're indirectly related. Everybody recall that? All right. Now, how does that relate to work? Well, pressure has a force component in it, yes. And a change in volume would imply a distance for your gas. Everybody good there? Okay. Now, let's picture in our mind a balloon filled with gas. Let's recall that the gas is our system, everything else is our surrounding. When the gas expands, what happens to the volume? It increases. When the gas expands, it's doing work. It's exerting a force over a distance on the surrounding. Everybody get that? It's doing work on the surroundings. Now, if the system contracted, if the gas became closer, particles became closer together, then the system, you could think of the system pressing in, doing work on, the surroundings pressing in on the system, and so the surroundings do work on it. Are we good there? All righty. Now we're back into familiar territory. We're using words that you've heard before, exothermic and endothermic. And here's that arrow showing you the direction of flow of energy. If something is exothermic, that means the system has lost energy to the surroundings. The change in energy of the system would be negative. The change of energy for the surroundings would be positive. And together, the change in the universe would be absolutely nothing. So the energy lost by the system, as evidenced by that negative sign, is gained by the surroundings. Now, the reverse is true for an endothermic event. The system has energy coming from the surroundings, so the arrow is going into the system. And so the energy change of the system is positive, while the energy change for the surroundings is negative. Now, most commonly, we're going to talk about this in terms of a chemical reaction. Here is a chemical reaction that we can talk about. The system in this case will be the elements carbon, oxygen, and the compound carbon dioxide. The surroundings is everything else. If we look at the internal energy, the elements have more internal energy than the compound does. An energy diagram looks like this. Here's the energy of the reactants. Here is the energy of the products. Energy had to exit this, and so the sign of the heat lost would be negative. And if we reversed this reaction, so now we have CO2 decomposing into carbon and oxygen. The reactants have less energy than the products. Energy must enter the system, and so it is an endothermic process. Okay.